Good evening, everyone. We should. Hello, Vivek.
Hi.
Can we have a, screen sharing test first?
Yeah, 1 second.
Okay.
Oh, is this 1 second? Is the screen visible
Yes.
now?
Yes, it's visible.
Okay,
Okay.
okay, okay, okay.
We'll wait 2 minutes and then Abhas will introduce and we can start.
Fine.
Hello, am I audible? Hello. Yeah. So
Yes.
sure. So if we'll start in 2 minutes as people are still joining. So like let it settle for at least.
Perfect.
So any question you can type in chat. We'll take it after the end, or if you have a very important doubt that you can't understand the rest of the talk, then you can ask in between. So I think we can start. So we'll thank Vivek Shukla from MSA team to who is a physics major. He'll give a talk on the exclusion zones in water. The stage is yours, Vivek.
Okay, thank you, Abbas. Am I audible?
Yes, you are audible.
Okay, perfect. So I hope everyone is doing fine, and I assume that most of you are from first year and probably second year. So, so at last you people have joined the college, and it must have been a long wait. I remember when in my first year used to attend these talks, which used to happen in the lecture hall complexes, and usually in the late night after 9 probably, because by then everyone would have been free. So I earnestly believe that these those days will come again, and you people can participate here as well. So by this, I think I should start. Means, so the title of my talk is Exclusion Zones in Water. You must have read the abstract. And so I'm not that of 10 pointers sort of guy. So you can please don't expect much from me, but although I've prepared much. And I used to remember that when attending talks, I used to understand very little less, and subsequently after 6 months or so, I stopped attending the talks. कि चलो कुछ समझ में तो आता नहीं है, what's the point in attending those talks? So my sole purpose would be that when you leave, you should have some takeaways. So with this keeping in mind, let's begin. So I started this work with Dr. Anant Venkateshan. This is a pretty simple experiment. There is nothing so non-trivial that you won't be able to understand it, or you won't be able to do it on your own. And I would start with a quote that discovery consists of seeing what everybody has seen and thinking what nobody has thought. This was quoted by Albert St. Giorgi, and he won Nobel laureate for discovering vitamin C. So he basically isolated vitamin C for the first time, and was also associated with citric acid cycle. And so in this order, in this fashion, I would present my talk. I would first introduce what this exclusion zone is, and then I would go delve into the non-metal hydrophilic interfaces, metal surfaces, and then some results. Finally, I'll sum up the work, and then I'll give a brief critical analysis. So let me just show you a video. So if you can see on the left hand side, it is a surface. It can be any kind of surface. So I'll explain in a while that what kind of surface it is. And if you see on the right side, these are solutes. Solute, and here these are colloids basically. So these colloids, when kept near the surfaces, they are excluded. Basically, this is a hydrophilic surface. So the colloidal and molecular solutes are excluded from the vicinity of these surfaces, and the distance, basically this distance is not very small. It extends up to 100 micrometers or 250 micrometers, and 250 micrometers is not a small distance. It's 1/4 of a millimeter, which you can even see with your naked eye. So I hope you must have got an idea that what this exclusion zone is. The exclusion zone is the distance, this region, this where the colloids are excluded from the surface of an hydrophilic character. Now moving forward, I'll begin that this is the water molecule H2O, which you know, and if these molecules, when in normal drinking water, these molecules are sort of this way, so we call it bulk water. And if this water in totality is kept near the hydrophilic material or hydrophilic material, some part gets excluded. So this zone, I think I hope that you are able to view the third figure. So this zone is called the exclusion zone, and rest of the region, this is called bulk water. Now, water molecule has basically zero charge, means it doesn't have charge. And if you see, we'll get into this, that how this charge separation happens. So, and where does the energy comes from? So, but when water, I was saying that water molecule doesn't has any charge, but when it loses a proton, uh, or in the hydronium ion, basically the it gets a charge. So easy water is a negatively charged region, and the bulk water is a positively charged region. And just giving a brief overview that how what is happening here. So how does this happen? So where does the energy come from? The energy comes from basically radiant sources, sunlight, maybe. It basically comes from photonic sources. Anything, it may be IR, it may be sunlight. It does not occur due to heating, you must remember it, but it occurs due to uh, photonic sources. And this is the, if you see the honeycomb sheet, it is the basically unitary structure of this easy exclusion zone layer. And this ice sheet resembles closest to the atomic structure, that how this exclusion zone is. Now, there are three more things that I have to discuss. First is a droplet, bubble, and a vesicle. So how does this exclusion zone looks like in a droplet, in a bubble, and in a vesicle? In a liquid droplet, you can see positive region here, negative region here. So this negatively charged region is the exclusion zone. Similarly, in the vapor, and if we combine this liquid and vapors, and so we term it as a vesicle. So basically, in a boiling water, let's say there would be uh, there would be both, like basically droplets as well as bubbles. Now, to raise some questions, I hope you must have got some idea that what this region is. Then only it's favorable that I should move forward. And I also should raise some of the questions that if you have seen that there are, why do clouds coalesces into discrete clouds means all the water vapor evaporates, and there should be a sheet of cloud and not a discrete set of clouds scattered here and there. So why do the water vapor coalesce? And I mean, how come humidity inside the cloud is 100% and right next to it is zero? So how does that happen? If you have also seen lightning and thunder, so I mean, how does water and radiant energy separate charge? I mean, charges form because of the water, and because when it rains or is going to rain, or because of the clouds, lightning and thunder occurs. And if you also see the jello basically is protein, and there is 95% water, and none of the water falls out. How does that happen? How does the coin floats, though its density is higher? Uh, Please mind that the coin must be kept horizontally and not vertically for it to float. And uh, so so basically, some people uh, may give the reason that it is because of the surface tension. But molecules on the surface are kind of hooked together, so that you have only 2 or 3 layers that are different from the rest, not all the layers. Means surface tension is because of only 2 or 3 layers. But the exclusion zone which I am talking about, or which Professor Pollack uh, has proposed, it is of millions of layers. So how does that happen? So to answer these questions, we'll take up questions and we'll try to answer them. That is, this exclusion zone phenomena which we saw in the video is general, or it is exclusive? And second question is this zone really physically different from bulk water? Anyway, we have seen the images before, and we see that it seems that it is different. And can water so this ordered structure, basically this exclusion zone ordered structure, can it explain some anomalies? I'll tell you what the anomalies are later. What energy creates this order? Basically, we also saw that it can be photonic energy. And what are the critical issues and why is it important? So to answer the first question, uh, I looked into some surfaces and some solutes, and it was found that a lot number of surfaces and lot number of solutes were showing this kind of phenomena. For example, polyvinyl alcohol, polyacrylic acid, polyacrylamide, polyHEMA, collagen agarose, polymers example Nafion, even the biological specimens like proteins, surfaces of muscles, and solutes such as polystyrene, silica microspheres, red blood cells, bacteria, even the ash and dirt which you can get anywhere in the campus, fluorophore, albumin. Albumin, I think, is a protein. I think, I'm not very sure. And so we started. I mean, I did not complete this experiment. I'm still in the process of doing it. So the professor Pollack started and doing these experiments with these various surfaces and solutes, and he sort of plotted the time lapse time scale, and he started to do various measurements to answer these questions. So here you can see this is acrylamide, PAA we call it, and here the exclusion zone, this is a gel which we create in the laboratory, and it is excluded up to 200 micrometers. So this is basically the exclusion zone. This is the gel on the left hand side. And in figure C, here we can see the time course of exclusion of albumin. So the exclusion zone, which is the ordered liquid crystalline phase, it also grows. I mean, if you can see at 0 second, 10 seconds, 360 seconds, and 1000 seconds. So it has grown. And further, a potential measurement was done. And this y-axis, you can term it as a, so this here, 0 is the surface. So you can see at 0, there is a gradient. There is a steep gradient, and which shows that charges have been excluded near the exclusion zone and bulk water boundary, if I'm clear. Now, NMR, IR and light absorption spectrum experiments was also done. So if you can see the B figure, the middle one, so this is the gel phase above, and below is the water phase, and this small region is the exclusion zone boundary. So exclusion zone, and in this exclusion zone, now before you understand that what does this figure denote, you must also understand what does NMR do, means how does it work. So NMR basically it tests molecular freedom, means you perturbate the molecule with the magnetic field and see how it can rotate or not. So this is basically a lighter picture of how does an NMR work. So basically you perturbate it with a magnetic field and see if it is still possible that it can rotate or not. So basically molecules were found to be constrained. They were not basically free. So this is what we saw in the middle picture, that if when we did NMR, and we found that the exclusion zone was basically molecules in the exclusion zone were constrained. Second is IR, and this is the IR radiation image of a Naphion. Naphion is basically a polymer, and when we took the IR image, we found that different regions were of different intensity, different light intensity. So, which clearly shows that they must have uh, different different properties, and basically different absorbance properties. Now, there were also experiment of absorb. This was the plotted between absorbance and wavelength. I'm not able to uh, pronounce it well. Absorptions and wavelength. So uh, when if we come closer to the exclusion zone and exclusion zone ZEL boundary, we see that peaks start occurring in here, some around 100 here, 250 to 70 micrometers. So this can be seen in the context that absorption is defined using two things, basically temperature and emissivity. And so this region must have some particular set of temperature into emissivity criteria. So these things were done to establish that this zone really exists or not. Although it is still debatable, and to basically to move forward, I have one story to tell that in the 1970s, the Russians discovered a polywater thing, and the polywater. It was also proposed that this polywater has very uh, different properties and all, and they were, and the United States, US people were quite anxious and about it because the Cold War was going at that time, and later it was found that that was nothing, and so there was a controversy, and someone also proposed that water has a memory, so that was also a disaster. Now, to sum up, the last two slides where I showed that NMR, electrical potential, IR, absorptions. So, first of all, NMR, it tests molecular freedom. So, we found that easy molecules were more constrained. And by IR, we found that EZ molecules are more stable. We can see more darker picture. If you can see the image here, so here near the exclusion zone, it is particularly dark. Now, second is electrical potential. So when we measured the electrical potential, we got gradient. So the gradient which we saw in this figure, it implies that charges are separated. And the exclusion zone has negative charge, which we saw in the earlier figures also. Third is the light absorption spectrum. So it distinguishes structures and electronic states. And for Naphion in the previous figure, we saw that exclusion zone absorbs at 270 nanometer. Now there was also experiments done on viscosity, but due to paucity of time, I haven't included it in my slide. So there was experiment done for falling ball viscometer, and it was found that this exclusion zone is more viscous. And there was also experiments. There was also uh, polarizing microscopy was also used, and to check that if these molecules are aligned or not. And it was found that EZ molecules are really aligned. So if you look back to this figure, basically this one, now you can see that EZ water has negative charge. it is excluded from the surface, and these molecules are aligned up to millions of uh, nanometer. I think nanometer would be a right denominator. Now, so yeah, I have included in this slide also. So in 1949, there was a paper, The Depths of the Surface Zone of a Liquid by J.C. Henniker. Here he talked about various oil surfaces and all, and it is a review paper if anyone wants to read it. It's quite interesting a read, so one can go through it. And Albert St. George, with whose quote I started, also said that life is water dancing to the tune of solids. So, and this exclusion zone phenomena was basically proposed by Thomas Hardy in 100 years back in 1912, and he termed that fourth phase of water, that this can be also called fourth phase of water. So to conclude, exclusion zone has negative charge. It is like a liquid crystal. It is a region that excludes solutes, has negative charge, liquid crystalline, and extends very far. And Thomas Hardy termed it as fourth phase of water. Now moving forward, so there are some kind of anomalies. We talked about gels, and we know that. We expect a gel to grow. Basically, gels don't dribble, and what behavior do we expect from a liquid crystal? So crystals can grow like icicle and crevices of jello. There is no dribbling in that. And crystalline water, basically, this water, AZ water, which we talked, is also gel-like. And using this polarizing microscopy, we also saw that in
Sir,
yes.
Thomas Hardy was the same mathematician which was in Ramanujan's story.
No, I don't think so. He's the different one. He's the different. I have to check.
Okay.
Uh, but I think so. He's the different one.
Because the time is very similar, I think, in 1912.
Yeah,
From English
yeah.
Royal Society. Yeah, I will check.
Okay, so it's a that was an intriguing question, and there is an author also named with the name of Thomas Hardy. So I also get confused that which author he is. So we were talking about gels basically. So this crystalline water is gel-like. It is consistent. We have seen these layers are aligned, and denser objects, they don't sink. And so this crystalline water prevents protons from penetrating. If you see here in this bulk layer, these are protons. And so you can also see that this positive and negative charge arranged here, you can imagine it like a battery, that positive charge on the right side and negative charge on the left side, and you can imagine it as a battery. And so this crystalline water, it prevents protons from penetrating, and hence it leads to a formation of a battery where charges remain separated. So uh, this explains that this behaves like a liquid crystal, means it shows properties which a normal liquid crystal would show. Now, second important question was that what charges this water battery? So when once I was giving this presentation earlier also, so I said that sunlight charges this water battery, and the professor there were three professors in the committee, and they started laughing that how do sunlight, and if you do the experiments in the lab, then how does this experiment happen? So then I corrected myself that uh, basically radiant energy, anything which radiates energy like UV is visible near infrared wavelengths, of which is of UV visible or near infrared wavelengths, it can induce exclusion zone growth. And we also saw the IR uh, effect of IR on exclusion zone and in the previous figure. So IR is particularly effective. Now, so the photons basically charges this water battery, and the effect goes beyond mere heating. Means it is not due to heat that this exclusion zone grows. And solar energy builds order and separates charge effectively, creating a battery. And there is also a hydrogen bonding versus thermal motion debate. So I'm not elaborating here, but to conclude that this water battery here is charged by radiant energy, radiant sources like UV, visible or infrared, like for example sunlight, or if you are doing in a lab, you can use infrared light, near infrared sources. So this concludes our first section, that is non-metal hydrophilic surfaces. So this was a lot of chemistry and bio sort of thing. Now coming to metal surfaces, so it was after 10 years, means Pollack started doing these experiments in 2003 paper. So 2003 he had a breakthrough, means where he told uh, where the world started knowing that this sort of thing is present. Means, he started gaining attention, and only after 10 years that uh, he and other people started delving into metal surfaces, that do metals show these kind of phenomena. So and the answer which he found was that yes, metals also show this phenomena. And uh, a various basically a specific setup was designed for a metal, because for non-metal surfaces, or for colloids, or for that sort of surfaces, you can just put water, prepare a gel, put colloids into it, and it gets exploded. And it's not that simple for a basically metal. uh, you have to prepare a setup. So a setup was prepared, which you can see in figure A, and a lot of other setups which I have not included in my image. And here figure B shows the view of pH dye near the zinc surface. So the darker regions, they show the exclusion zone, and this lighter region, it shows the uh, bulk region. And this is also a zinc surface, and you can see that water molecules are excluded near the surface. And how does this influence metals? Means what does why do metals should care? Means I mean, water molecules should get excluded or whatever. So basically, in the recent literature, work function values for various work functions were also obtained, and it was shown that they have particularly impacts in the electrochemical series or galvanic series. And same potential measurements which we did in the previous section, here also for metals also potential measurements were done. And so this is the diagrammatic representation, which you can see the zinc surface, OH ions and protons. Now to sum up, the zinc, aluminium, lead, tin, and tungsten, uh, they showed exclusion zones, and nobler metals like platinum and gold did not show any zones. So the more active and corrosive metals, they presented larger exclusion zones. And uh, I was talking about that why should metals care? So it metals should care because this phenomena provides a greater understanding of metal surface electrochemical processes and the electrical potential measurements. It showed that high concentration of positive charge exists near the reactive metal surfaces. So basically protons, which I was talking about in the previous slide, and the high pH values seen beyond those near surface zones imply that high concentration of OH minus groups. And this table here, which I have included, it shows that 3 experiments were done and uh, work function values were plotted, and it was averaged, and it was found that they corroborated with the theoretical values. So the substantial changes in work function measured here are due to complex structure of water in the vicinity of metal surface, and there were very little difference found with what theoretical predictions have given. So what is my experimental setup? So I sort of prepared a gel, and I so this is the third part of the talk, that how I am doing my experiments. And so here I prepared a gel. I using a glass rod. I uh, kept some hole in the middle, as you can see, and here I put some microsphere, and then in the uh, microscope I then I observe the exclusion zone. One second, let me drink water because yeah. So by this simple setup, what are the results that I got? I'll show you. So these sort of results I got, these are not very perfect, but yes, you can see these green regions. They are basically the exclusion zones. That these things from the surface. And what is the surface? This circle is the surface, and if I put my colloids here, they will exclude and move away. So as you can see here, these are the colloids which will move away from the surface, and these were the results that I obtained. So as you can see in this figure, these are the colloids, and this region is particularly very much excluded. So I'm still underway in doing these experiments. And now, how does this polyvinyl PVA, it is a gel. So how does this PVA, polyvinyl alcohol gel, uh, uh, this molecule's concentration, how does this affect? And it was measured using different microspheres. There is one type of microsphere was carboxylate, and another was amidine, and you can see that exclusion size for the amidine one was it was decreasing with PVA concentration, and similar exclusion zone size versus pH of microsphere solution graph was plotted for both amidine as well as carboxylate microspheres, and uh, it was seen that as the pH increases, matlab from 7 if it is increases, or if it decreases, the exclusion zone size increases. I mean, near 6 here, the exclusion zone is 0, but after 7 or below 6. So this above 7, it is carboxylate, and below 7, it is amidine. Third figure here is C. which is the results obtained from microspheres of opposite charge. So, do charges matter? Means, I mean, if you put charges of opposite, if you put colloids which are positively charged or which are negatively charged, and we can see that there was not much of a difference. Means in both the figures, you can see there are exclusion zones. So charges don't matter as such. Uh, Salt concentration, does it affect the microsphere, the exclusion size? So as you can see in B figure, so the same sort of plot we get, which we got from the PVA concentration, and pH we already saw, and what is the next one? Microsphere concentration. What happens if we increase the concentration of colloids, or basically the microspheres? So does that, so not much basically, because it is a property of water to exclude those colloids. So it is sort of a straight line curve. Means these points are plotted, and if you connect these points, you can see uh, not much of a difference in the exclusion zone size. Moving forward, so I also plan to prepare some colloids using emulsion polymerization, and uh, I was in way of tuning PVA concentration, salt concentration, microsphere size. How does microsphere concentration can change it? If I can bring in two types of microspheres. Microspheres are basically colloids, if you can get my point. And I also sort of tried using a PhD dye. So, and the experiments which ascertain the generality of the experiment, I haven't done it myself yet. So I would like to do it, to do these experiments, NMR, IR spectra. So we have NMR here in CAF building at ISA, in Kavita Durai's ma'am's slab, and fluorescence spectroscopy. So Ramesh Ramachandran, he is in chemistry department, so he has a very nice work in spectroscopy. So basically, this work is pretty interdisciplinary, and you have to move from lab to lab to get your work done. And so now coming to the penultimate section. So there were another alternate theories that propose what might be the reasons for this exclusion zone formation, and they told that this Skur, uh, a professor, uh, he proposed that this exclusion zone formation is created by forces arising from a concentration gradients of OH minus and uh, protons, and a salt. So these are the naphions, and so if you can see, this is a homogeneous case and this is a heterogeneous case, and a charged particle here, it attracts counter ions, and uh, via the electric field. So work is still on, and I haven't gone through it much because it is an alternate proposal and has not been studied much. So now in the abstract, I asked some questions that why do pressure cookers whistle? So I would like to answer them because I hope that much of the previous part which I talked about, you might have understood or might have not understood. Oh, it was relatively simple, so I don't think that you might have not understood, but still you might not use it further. But I think these general questions, these you can take away with you, you can take with you. So why do pressure cookers whistle? So how, so we know that sounds are formed from mechanical vibrations, means, and we saw in the first slide there was a droplet, there was a vapor, and using a droplet and a vapor we form vesicles. So when we heat water, vesicles are formed, and due to when it starts boiling, it may fuse or fracture. So when it starts boiling or bubbles break, they release protons, and which build a repulsive pressure inside a cooker, and which pushes the vapor through the vessel at high speed. And I mind you that these protons do not appear just until at the point that boiling begins. So if you have seen a pressure cooker and the whistle, so if you try to pull up the whistle and see that uh, the sound comes or not, uh, it does not come until the boiling begins. So if you push it up and see the sound comes or not, so it the sound comes only after the boiling begins. So the pressure cooker whistles because of these protons. So bubbles break and protons are released, which build repulsive pressure. Second question was that why do pollen grains dance in muddy water? So this is Brownian motion, and uh, so uh, I thought I will not elaborate it much on that. Means it's relatively easy. Now, third thing is quite important, that how does cloud form some alluring shapes? Now we see that uh, Richard Feynman gave this quote like likes like, and when we put two similar charges in the water, so we can see the positively charged get accumulated here, and these two molecules would want to come near each other. So this is what happens in the clouds also, means they form into discrete shapes, and they come closer, and they do not remain scattered or in a homogeneous phase. Now the last question is that why does water shows maximum density at 4 degrees Celsius? And this is a very important question. Means uh, what is the importance of this 4 degrees Celsius? Means why 4, not 3, 2, 1, or why this thing? So cooled water has several phases, each with different density, and we can see that exclusion zone has higher density than bulk water, and which has a much higher density than ice. That is why ice floats in water. You can see in the first figure that uh, volume of water in ice is relatively higher, so its density must be low. Now, we started cooling water from here, and you can see this dotted line is of zero, is of 4 degrees Celsius, and the infrared gradients, they were increased, and they started building exclusion zone content. And since this exclusion zone is a liquid crystal, and we know that crystals grow, so the volume started shrinking and density started increasing. And when the cooling it reached the threshold, the exclusion zone, they started transforming into ice. And so there were patches, means little patches that they started replacing exclusion zones. And since ice is bulkier than exclusion zone, the volume starts increasing. So now where does 4 degrees Celsius comes into this picture? So we know that water freezes at 0 degrees Celsius. So at zero, all we have is ice. Means at just below zero, all we have is ice. So water must have a maximum density above zero. So we started moving above from 0, 1, 2, 3. So the temperature was estimated like if freezing occurs at 0 degrees Celsius, then patchy ice might be forming a few degree higher, and so 4 degrees Celsius would be the temperature of minimum volume. So first the volume started decreasing and then volume started increasing, and all that because of a exclusion zone which had a higher density than the ice. So the key takeaway is patches of exclusion zone, patches of ice were formed from the exclusion zone. These are the references for non-metal hydrophilic surfaces, metal surfaces, uh, critical analysis alternatives. These are some books, and so this is all from my side. I think I was able to deliver into perfect timing. Means I thought abhi आधा घंटा ही हुआ होगा. So if you have any questions, please feel free to ask.
Thank you, Vivek. That was a very interesting talk. I see that Sahil Shah has asked a question. Maybe you're around, you can ask.
Okay, let me see.
Okay.
Okay. Yeah, I can see.
So what is the width of?
Sahil has asked the
Yeah.
question, what is the width of the exclusion zone and what does it depend on? So yeah, the width of the exclusion zone, as you can see, were from 100 nanometers to few micrometers. I mean, uh, let me show you. So here it was up to several hundred micrometers. You can, I also showed you in this slide. So here it is of the order 200 micrometers. And here it also went up to 270 micrometers. So 270 micrometers, it's like 1/4 of a millimeter, and which is also visible through a naked eye. So second part of the question was that what does it depend on? So it depends basically. Uh, 1 second. So basically it depends on the intensity of the light which you put, or intensity. For example, in the zinc here, the more infrared radiation was put, and you got more. The exclusion size was increasing. So as we saw here, it was not depending on concentration, charge, and this solute size or microsphere concentration. It basically depends on the intensity of the light which is falling on, which is falling on. I hope it answers your question, Sahil. Okay, anybody else has a question? Anything means I think it's important that you ask questions, anything trivial or as important, related, unrelated. Or if no one has questions, then I think that was from my side, and I would not like to bore you much.
So I guess that's it. Uh, yeah. Uh, okay. So that thank you once again. Thank you for that engaging presentation, Vivek. It was good. So I guess we'll wrap it up here. Thank you everyone who joined. So see you next
Okay,
time.
and
Bye bye.
thank you everyone
Hello.
for Speak.
Thanks a lot.
Okay, and thank you everyone for attending. I didn't thought that so many people would come after 2-3 months after the college has started. So मतलब 2-3 महीने में तो सब normalize हो जाते हैं. Okay, ठीक है.
So
All the
thank you.
best. Bye.